Hello. Let me know if you can hear me. Welcome back. I have not heard from Dorant, so I do not have a way to use Zoom so efficiently. I'll do my best to resolve for tomorrow or next week. But at any rate, if you need to speak with me, just text me in WhatsApp. I gave you my number, and we can make arrangements to speak if you have questions. All right? Bonsoir. I'm just going to wait for more people to arrive. I'm here, just waiting for people to log in, join us. Okay, I was just sending an email. Only 10. Bonsoir. Remember, if the screen gets blurry, just refresh the page. Unfortunately, again, my captions did not appear in the video. YouTube routinely changes its settings, and I am the only one, and I have no advisors on how to use things. I'm going to have to figure out how to get the captions to automatically generate. I've clicked one option that might work. Let's try this on this new stream. Otherwise, please let me know if you are not following or understanding, and I'll do my best to answer your queries. So from now on, you can find all the communication in all the videos in the same playlist, MBAUNDHLive. Okay, so they'll all be posted there with the dates. So I left off with this exercise. I asked you to have a look at it, and in the last 2 hours you might not have had time. So let me give you some time to attempt this problem, and we'll discuss it. I have to see what is happening. I need to try this again. Let me refresh things on my end. Sometimes things freeze up. So if it looks like the thing that is viewing is different from what I'm saying, refresh your feed. And let's see. Why is it not viewing? It's kind of frozen on my end. There we go. Okay. Too many things to learn. So little time. Okay, so this problem, example 4 is what I want you to try. A food scientist is planning to conduct an experiment to investigate the effects of different redox agents, different types of flour, and different dough mixing methods on the quality of loaves of baking bread. So there are 3 redox agents, 3 types of flour, and 2 mixing methods. These are combined in the experiment. In order to assess quality, each loaf of bread will be assigned a score of 1 for number 1, flavor, number 2, loaf volume, number 3, loaf density, and 4, crumb texture. So the questions are, how many factors, how many treatments, and how many response variables are there in this experiment? So you can give me your responses in the feed. Remember, if the screen freezes, can everybody hear me? Can you hear me? My computer says yes. Okay. So what do we have? What just happened? The feed is different from my view. Okay. Very good. What do you get? Very good, thank you. Great. So, what's the answer? Questions. If you have difficulty, let me know. I can answer questions. Okay, 3 factors. What else? So there are 3 factors: redox agent, types of flour, and mixing methods. So those are the 3. And each has a different number of levels. There are 3 redox agents, 3 types of flour, and 2 mixing methods. So combining those, just like we did above, what we did above was compute the number of treatments. I drew a box and essentially considered 2 levels times 2 levels so that each could be combined. Okay, each one was shared with the other. And so that was 2 by 2, which made 4 treatments. It's 2 levels times 2 levels for 2 different factors. So we're going to use the same principle. Exactly, some people have already figured it out. The same principle below for number of treatments, 3 times 3 times 2 is 18. So this is 3 factors, 18 treatments, and what are the response variables? What are we going to observe as the impact of the treatments? Flavor, loaf volume, loaf density, and crumb texture. So those are 4 responses. For some reason, my video does not update at my pace. Very strange. Okay. So if you see that what I'm saying is not matching what you view, you have to refresh the screen. So I just had to do my own refresh to see. The number of responses are here. You see? These are all responses here. There are 4 of them. Do you see that, Jessamine? To the treatment? So there's, what I'm going to do is I'm going to illustrate this to see how it works. So the calculation of treatments is just that above, this using this formula. Treatment is the levels of factor 1 times the levels of factor 2, as many factors as you have. In our case, we have 3 factors, so we just multiply their levels. That's why we get 3 for redox, 3 from types of flour, and 2 from mixing method. And you get 18. So how do we visualize 18, just like we visualized 4 treatments above? Well, we can do the same thing and think of a matrix. Okay, so the matrix would look like, I would have, I'm going to make this a bit bigger. So redox agent, and there's 3 types, right? And then, what's the second one? It's called types of flour and then mixing method, okay. And then types of flour. One, 2, 3. You see? And you would combine to make a matrix combining what first kind of redox agent with the first type of flour here, and then redox agent 1 with type of flour 2. Okay, so how many do we have there? We only have 9. So the third factor is mixing method. So using mixing method 1 and combining the factors in a table or matrix like this, we have 9 combinations or 9 treatments. Now we just replicate that for mixing method 2. You see? You see, this one makes 9 different treatments, and so does this. So 9 and 9 is 18. So that is that's going to help you get the number of treatments, and then you can think about, I didn't ask you about this, but for each combination, in this case, here you're going to use redox agent 1, type of flour 1, and mixing method 1. Maybe you should make a few loaves, because there might be other variables that you can't control for that might influence things. So maybe you want to make 2 to 5 loaves of each combination of factors. All right, and then you can compare. You have to get a taste tester to compare the lows for those responses. I'm not going to get into much more than that. The focus here was just to demonstrate how many treatments in the experiment. All right, I have a question for you, unless you have any questions for me. Why is there no control group? I spent some time talking about control group. Why is there no control group? Question. Why did we not use a control group? That's right. Because we usually, although we could use a comparator group like a control group for non-human subjects, in general though, for non-human subjects, it's not a given that we need a placebo control group. It might be different if you want to compare one type of treatment to another type. And like an original type of treatment or a current treatment against an experimental treatment, and you could fix that and call that some sort of as a control, refer to that as a control, but that's not the same as a placebo control group on human subjects. Okay. The subjects here are the loaves of bread. All right. So you guys didn't do so bad with that. Questions or comments? So what you can do is take a screenshot or, check back with this video. My goal will be to put timestamps in the video so you can easily review the video. Timestamps will appear in the description, and you can click on them, and they can position you in the part of the video that you want to watch. Okay? So I'll try and do that. Right, your answers are right, Patrick. Right, you guys are right. So it's not, the point is that you don't need the placebo control group. Very good. All right, so I did talk about randomization earlier. And that leaves us here with experiment 4. This is just another example of randomization. So this is an experiment designed to investigate the best way at promoting energy conservation in households. I introduced 3 different treatments, and this is on human subjects. This is households. For that reason, one of the treatments must be control. So the idea is going to be to conduct this properly with what we've learned so far. The investigators would invite households to participate in this study voluntarily. And let's say at 60 households, they decide that's enough to conduct a study. So they take the households and they number them because there's 60. They number them 1, oops, so if there's 60, the labels have to be size 2. 01, 02, 03, 04, all the way to 60. And the households are selected. The first 20 can go into group 1. The second 20 randomly selected will go into group 2, and the third set of 20 will go into group 3. Or, as we did with the aspirin, the physician health study example, I randomized 1, and then to the second, and then to the third, and continued. Either one is fine. Equally good. The point is, we first label our households, and then use a random number generator to choose households. So this is our randomization. The households in group 1 will receive treatment number 1. Household 2 will receive treatment number 2, and household 3 will be the control. And then what we do is we look at total energy conservation from the beginning. So here at this point, the electricity meter So electricity consumption for the last month could be recorded here, and by the end of several months, again, the energy or the electricity consumption will be recorded off of electricity meter in the household. And the group with the greatest change in energy consumption would be deemed the group with the better treatment. Okay? All right, so what could these treatments be to ensure that this is a good experiment? Well, the household would have to be notified at the outset that they are going to be part of a study and that someone will come to record their electricity consumption either on their meter or using an electricity bill, possibly, for the past month. And they would be told that they will be visited routinely to measure their electricity consumption or to record their electricity consumption. The control group will only get a visit at the beginning and at the end without any intervention in between. That's a possible example of a control. so that they know they're being visited and their energy consumption is being recorded, but otherwise there's no other interference with the household. Whereas in group 1, this household is told that their meter will be, and they will observe that their meter will be recorded every couple of weeks or on a routine basis. This group will be told, it's treatment number 2, that they'll be taught how to read the meter themselves and how to maintain a chart of consumption. So this provides some sort of feedback to the household on their regular use of electricity. These are intended to be behavior modifying treatments so that then we can compare without any kind of behavior modification, is there an improvement from either of these treatments, either of these approaches to energy conservation. So I don't have any numbers to share with you, but you can just imagine that probably all households will be much more conscientious about consuming energy in the household because they know they're being watched, and that's why we have to have a control group. So consumption will go down through all of them, but the question is there a significant difference between these two or these two compared to the control, so that you can say that there are sincere ways, there are actual methods of promoting energy conservation. Does anybody have any questions about that? So it's just to show you how to randomize. And in the annotations, in the annotated notes, I provide this description as well. Let me show you that. Again, I know, I can't believe it. No, sorry. I'll just get out of here. I think the file's too big. All right, so you can see that I've marked up the notes in the annotated version. So any comments? So as I explained, for good experiments, they need to observe the 3 R's: representation or control, randomization, and replication. So the last point to talk about is replication. So replication refers to the fact that we need enough houses in each group. So in this case, we used 20. It was determined that that was enough. Statisticians would help with that kind of thing. What number is enough? In the loaf study, it should be determined how many of each type should be made for replication purposes. And the goal of that is to allow for variation to appear. So if you have many houses, right, you might be able to see, if you have many houses, you'll be able to see if there's systematic differences between the outcome of this group and the outcome of treatment group 2. If you only had one house in group 1, And the house happened to be very energy conscious. They don't want to waste money on energy, so they keep the lights down. They turn off the lights when they leave a room. They have energy efficient light bulbs and things. Then the fact that the idea that this house is energy conserving house is really what you're picking up. You're not picking up the effect of treatment 1 or the meter reading that's going on. And then how would you compare that unless the other, if there's only one house here and it was the same, that would be maybe something you could compare. But what if it wasn't? What if this house was more wasteful? Okay, this is more of a conservation house. This one's more wasteful. So what are you seeing? You're not seeing the effects of the treatment, you're seeing the effects of the type of household. So you want to roll that out just like we did in the physician study and make sure there's enough in each group so that you can see differences of the treatments and not just the differences in the subjects. Okay, so that's what replication is about. Some last comments on experimentation. Remembering that you want to be careful about hidden or lurking variables in experimentation. And I provide an example and ask you what you think. If we were to conduct studies using rats that we caught on our own, with our own device, by our own devices, we went out into a field and caught rats. And we used the first 15 that we caught. If we were to use these subjects in any kind of health study, what would be the possible lurking variable, and what would be the kind of bias it would create? These two questions go together. What answers did you provide for that, or what do you think? Is not a defined group affected? Be more specific, Jefferson. That you don't know, do you mean that you don't know the type of rat? It's not clear? So in fact, in experimentation, by cancer. So yeah, if you use them in a cancer experiment to see whether they survive certain treatments, first of all, what's done in experimentation is rats are actually, or rodents are actually genetically modified to have either certain defects or genes that in their DNA that create cancers. So they're actually created with cancer so that there's a level playing field, and then treatments are tested on them. But if I were to go into a field and catch some rats and test, first of all, impose cancer on them, and then try treatments on them, what could possibly be a problem with that? All right, so that's right. Ulrich says there could be predisposition to poor health, right? And then Caddy, yes, also health issues from some rats being injured. The weight of the rats, they run slower, exactly, Anouk. So this is the idea that lurking variable is the quality of health. The fact that they were caught in the first place made them slower, possibly by poor health or maybe by age. Okay? That would be a lurking variable in our outcomes. And because of that, what we're trying to test the effectiveness of treatment. If our rats caught in a field fare poorly against cancer and then the treatment, that would downward bias our results of the study, right? Our treatments are not going to appear successful. They will be poor or weak or have low results, downward biasing them. Okay, good comments. That's right. If they're sick, you could catch them easier. And it's not random at all. That's right. So there's going to be a systematic bias in the ones that you caught, biased towards the sicker, slower, unwell rats who might not do well with the treatment once cancer has they've been exposed to carcinogens or cancer-causing elements. Okay, the other point to make is you want studies to be generalizable. However, when you conduct an experiment, they might lack realism. You might be conducting a study in very sanitary conditions that don't mimic reality. So, for instance, we have been told that in the presence of the coronavirus that is linked to COVID-19, that we should be wearing a mask. However the mask is made, whether it's a surgical mask or a cloth mask, we were told would be sufficient. And some people have argued, wait a second, nurses and health professionals using masks, especially in surgery, use them in sterile environments. So if you take the results of using masks in a sterile environment and then tell everybody in the general population that they can use masks, that lacks generalizability because they need to be tested in the general environment. They lack realism in making those kinds of statements. Right? So studies about masks should actually be conducted on the general population. Even laboratories that look at particles passing through the mask. Also, those sorts of studies have to. Those environments also are all sterile. When people are walking around, you need to see how those particles move because of movement around them, like in the streets or in the malls or in the stores. So keep in mind, watching what's unfolding in front of us in this era of pandemic, I personally have seen very weak science. The time has been short. It's almost a year, yes, but there's been on so many fronts. The different stakeholders have tried to mount resources to study, masks, to study lockdowns, to study the effectiveness of vaccines. So there's a lot of things have been on, many efforts in the same scientific community, and it's been hard to be thorough, I would say. So yes, the more realistic the environment, the more meaningful. Actually, the latest studies have shown that people, reusing a mask can be dangerous, and I've known that from the beginning. I change my mask if I'm going to wear a mask. I will change my surgical mask, and the cloth masks have to be washed routinely, and that's the way it is. So those are my comments on realism versus sterile environments. So similarly, pilot projects. So pilot projects are smaller versions of an experiment that are preliminary, give preliminary results, and they demonstrate the value of proceeding with a larger scale study. And this is for getting funding, some sort of financing, if you get it through a federal agency or an international agency. It's useful to run a pilot project that doesn't cost as much, and then to get funding for the larger project based on your preliminary findings. Same thing with small-scale biology projects. Also, these with crops, we have to be careful about the realism of conducting studies on fertilizers or in the response of the yield of plants, conducting them in a laboratory setting versus in the natural environment. In the natural environment, they're going to face all sorts of different elements: the wind, the sun, the rain, cold, depending where you are, and pests. So conducting a study, a small-scale project in a sterile or a clean laboratory environment is not going to be the same. It has to be set in, also at a different stage, has to be set in the natural habitat to make sure that realistic or generalizable results are found. You have to be aware that what are the conditions that experiments have been conducted in, and whether they are, how they are generalizable to the public. And I've already given you an example talking about the mask. There have been some controversial studies on products, food additives like aspartame for sweetener, as an example. And it's questionable, how those products can be, the results of those studies are generalizable to the human population without the actual experiments being conducted. What it comes down to is something I've engaged in, are population-based studies. This is after the fact, looking retroactively at data over time to see the effects of, in the natural environment, of certain changes. So looking at the population at large, not in an experimental setting per se, you may in the larger population be able to find patterns. Okay, so that's obviously observational. But it will provide insight for the failure of experiments to be generalizable. And for example, what I've mentioned about, again, about the masks. So given that it was impossible to, it's unethical to study the effects of smoking on human subjects, directly imposing a treatment group against a control group for smoking, knowing the risks of the carcinogens of cigarettes. How was it that the Surgeon General of the U.S., after seeing the videos, came to the conclusion that smoking causes, very strong term, causes cancer? What did you write? So, although experimentation, to wrap this up, is the gold standard, it's intractable, it's impossible to do, in some cases for ethical reasons. It's infeasible to do because a laboratory setting is not the same as a generalized setting in the public. So it turns out, as I mentioned, the resolution is we fall back to kind of full circle, observational studies to see results. And this is what happened with the case of smoking. It was 40 years of studies, to say even more, 40 years of studies, prospective, retrospective, and animal trials, studies on animal tissue, all showing the same thing. I'm just going to write it like that. I wrote it nicer and longer in the annotated notes. So 40 years of studies, prospective and retrospective, in animal tissue studies, demonstrating a link. And those were experiments. That's what made it possible for the Surgeon General to make such a claim in the 1960s. Oops, let me try one more time to get that page up, because I said it so nicely over here. These pages won't open. Nope. I think they're too annotated. Sorry, I'm jumping around. Okay, so that's what made it possible, that all these studies showed this, demonstrated the same thing. That's what made it possible. And these were partly population-based studies. Questions? So just the sheer quantity of studies, and that they were done, these studies were done in different parts of the world. So different regions, different cultures, different people. So to overrule that it could have been some systematic bias that was causing people to be susceptible to cancer. There was a dose response effect as well. The more smoking, the worse the cancer. Okay. Any comments? So if you haven't seen the videos, you'll see all of that, and this will make more sense to you. Okay, I need to talk about other types of designs now. Okay, there's two other types of designs that are related that I like to discuss. One is the matched pairs design. And maybe some of you are familiar with the best example I have for the matched pairs. It's the Coke versus Pepsi challenge. Anybody familiar with the Pepsi challenge? Pepsi challenge is actually an experiment. So this is where Pepsi employs people to set up a kiosk. So this is a table in a popular, a well-trafficked place. So this is in maybe a fair or near a concert or near a festival. And Pepsi sets up a table and invites passersby to take the Pepsi challenge. They give them 2 cans of cola. They're unmarked, and they give one at a time. So they hand 1 can over, and the participant, the subject, will drink from the can, return the can to the investigator, and then be given the other can, which they drink from. And then they're asked to choose between the 2 cans which one they prefer. This is an example of a matched pairs design. To be an experiment, though, remember this experiment needs to observe the 3 R's. So R for representation, or control, R for randomization, and R for replication. So what I need you to do now is tell me what are the features of this experiment that qualify it as the matched pairs as a good experiment. This example of matched pairs is a good experiment. What is the representation? What is the randomization? And what is the replication? I'll give you some time to think about it. Anyone? Just take a chance. So how do we conduct this? We choose pairs of subjects that are closely matched as possible. One will receive one treatment and the other will receive the other treatment. Assign the treatments randomly, or randomly select a sample of individual subjects who will receive both treatments, and also the order in which the treatment is administered is conducted in a random fashion. So I'm giving you the tips there. In this case, in the Coke versus Pepsi challenge taste test, the control is the subject themselves. What's better than as closely matched as possible than the person themselves? From testing one can to testing the other, the person's preferences haven't changed, presumably. It's the same person. So that's the best control you can have. It seems a little strange, but that's the way it is. Another example of matched pairs are twin studies. When you study twins, identical twins, you can determine, you can distinguish between factors that are genetic and factors that are environmental, just personal preference, although that can be genetic as well. Conducting an experiment on twins where the biology is identical makes for interesting results because you can see if there's any difference in effect and the possible reasons for that that are not biological. So anyone going to tell me what's the randomization of this experiment? Does anyone want me to repeat the Pepsi challenge? I dropped my iPad. So the point of the matched pair is that the pair receives both treatments. In this case, the single subject receives both treatments being, here the factor would be cola and the levels would be Coke and Pepsi. The randomization of this experiment is something that's done in advance, where the cans of cola just have numerical labels but otherwise look the same, and the numbers indicate which one to use first and second, but somewhere someone has a list of which one is Pepsi and which one is Coke. But the order of which Coke and Pepsi are consumed is randomized from person to person. So the order which the cans are given is randomized. Replication, what is replication? Replication would be the many customers or the many subjects that appear at the kiosk to participate. So with those three components, we will call this an experiment. And Pepsi would have you believe that the results of the Pepsi challenge favored Pepsi over Coke. Although we don't know the truth. Okay, you guys have become quiet. A little bit quiet. So a match pair design is an example of what's called a block design. In a block design, okay, good. Thanks, Patrick. Okay, very good. Thank you. In a block design, we do not randomly assign all the subjects at once to one of the two treatments. Okay. First, we separate subjects into their blocks. In our example, like I mentioned here, the subject receives both treatments, right? So it's a block. But in more general terms, blocks receive both treatments. So I'm going to show you, here is the description of an experiment. This experiment is conducted, I'm going to make this bigger for you. And I want to hide this part. All right. So we're going to study the effect of a new therapy. I'm going to introduce a control because these are human subjects. And we're going to use a new therapy. We're going to compare it to an old therapy. That's the old treatment. And this is the new treatment. All right. I'm going to move this over a bit. Now let's say we got volunteers and we numbered them and we randomized them into groups. So the first group of however many subjects, the second group, and the third group were all assigned. Let's say I decided to put, let's say I put 50 in each group. So I had 150 total subjects. So my sample size is 150, and there's 50 in each group. And then group 1 will get treatment 1, group 2 will get treatment 2, group 3 will get treatment 3, and then I'm going to compare survival. So group 3 will not have, they'll just have a placebo, something that looks like the other treatment, but it's really nothing. Just maybe sugar, powder, or nothing, flavorless filling in the capsule. So this treatment here is for treating cancer, and it's known that women respond differently to the treatment because their hormone levels being much more complex. They're known to be much more reactive to the treatment. So if we just did this on the general public and we know in advance that women react differently than men, what would happen if we had a bunch of people, but it just so happened that this group turned out to be to have 80% women in it? It could happen, right? So we imagine in all possible samples of taking 50 from 150, it could happen. 80% could be women in that one. And what if, like, this one had 20% women in it? The fact that we know the treatment, I won't even mention this one, we know the treatment has a different effect depending on gender, we have a confounding effect of gender if this happens. So to avoid this completely, what we do instead is we pre-select women to be in one group and men to be in the other group, and we repeat the experiment for each block. So these are called the blocks. So we do the same thing to avoid this. This doesn't happen. What we would do instead, if we had 150, that would be, we'd have to divide out how many men and women there were. It might not be even. That's okay. If we have what we think is enough, what our statistician tells is enough. So let's say it turned out mostly women enroll in studies more often than men, it turns out. So let's say there were 80 in this one. This is the sample for women, and this is the sample for men. And let's say this turned out to be, okay? And this is what we would do. Now notice, the thing to notice here, it looks exactly the same, but I'm doing it twice, doing it separately for both groups because the blocks, each block gets all the treatments. That's the point. So men are a block receiving all the treatment, and women are a block receiving all the treatment. And I compare women to women and men to men. In this case, blocks make sense. Questions? So that's the most important thing, is that blocks receive all treatments. And we do this to control against a possible confounding effect. If we didn't do this, if we stayed with this over here, how could we fix the problem? Anybody have a suggestion? Where I had 80% women here and 20% women here. What would you suggest? How could I fix or correct for that problem? So to avoid that from happening, you'd have to you need more volunteers. And each volunteer adds a cost. These are people that you have to provide with the drugs, people that you have to monitor, people that you have to collect data on. So each subject carries a cost. Why would you want more volunteers when you can resolve the problem by blocking? So blocking is a cost-effective way to conduct experiments like this. Comments? Okay, any comments? So let me know if you have any questions about any of this material. You can write me an email, you can write me a WhatsApp, I can talk to you, I can understand French if you speak slowly, you help me out. And hopefully we'll have the captions working, so that might help you as well in reviewing these videos. And I will pull up the timestamps and I'll show you how to use them. Comments? No? Okay. So to comment here, as I mentioned, one of the treatments must be a placebo to control for the placebo effect of human subjects being studied. Question: how does a block design differ from a completely randomized design? Is there more information supplied? So what we've done is we've done a completely randomized design in one block and a completely randomized design in another block. And we've removed possible variation that will make it more difficult to notice differences, significant effects of one treatment over another. So yes, there is more information supplied. Randomization occurs within the block. And in general, the more the restrictions, the more information is supplied. That we're getting closer and closer to our variable of interest. I never, like right here, once I've divided men into a group and women into another group, I randomize between among men and randomize among women. When I divide 70 by 30, it's not an even number, but we'll just say for purposes, it doesn't make much of a difference, okay? Probably should have picked even numbers not to confuse you, but it's fine. We'll say it's fine. All right. So we're going to talk about samples next, and you'll see that this is going to come up again in sampling designs. And if you did watch the video, I mentioned something that sounds similar, stratification in sampling is like block design in experiments. One last question. What is the primary reason for using a matched pairs design or a block design rather than a completely randomized design? Which one would you pick? Now, which one would you pick? A, B, C, D, or E? So given the lecture, I kind of guided you which one to pick. That's correct. A. Very good. You got it right. The answer is A. Let's go over the other ones. So let me read A first. More precise conclusions about treatments can be obtained for the same cost. So we're not going to increase the cost. We're just going to split women and men, and we're going to get more precision in our results because there's less confounding and less variation among our subjects. That has nothing to do with the treatment. Okay, it has to do with their gender. If we pair or block, we can avoid process of randomization. No, because there is randomization in the block, so that's wrong. C, it is easier to assign the treatments to pairs or blocks rather than to individual subjects. No, because we're still within the blocks, we're randomizing two subjects, so that doesn't make any sense. Pairing or blocking effectively increases the number of subjects in the experiment. I just showed you, no, that's not true. I didn't increase the subjects in the experiment. All I did was divide. I pre-separated, I pre-blocked and separated men and women. I didn't change the number of subjects. It stayed at n equals 150. Pairing or blocking effectively increases the number of treatments. No, we didn't change that either. So the example that I gave you shows these four are not accurate at all. Okay, very good. Very good, all of you. Let's take 5 minutes break, okay, because we're at the halfway point, and I'm going to talk about sampling. Okay. Let's take 5 minutes. Get some water. And if you have questions, just write them down, send them to me, and I'll address them in the live stream. Or I'll answer your email, or we'll meet to discuss. This says 5 minutes. I'm back. How's everybody? Any questions? So what you can do when you review this week, you review the homework, and I think you'll have more than enough with the homework exercises this week. But if you do get into the midterm exams, you can start reviewing those as well. If you have questions of any of those, all you have to do is send me the question number and the document, and I can address your questions during the next stream or by email, or however you like. Okay, I'm going to continue. So we did discuss this first day, first hours of class, in designing samples. What is our goal? Our objective in statistics is to gather information, right, about a variable to make predictions about what to expect. That's the idea. We do that both with sampling and experiments, except in experiments we impose a treatment and observe the impact of the treatment. Again, to help us understand what to expect. So we talked about a population is the complete set of all items that interest an investigator. Population size is used as presented usually as capital N. This is a universal. It can be very large or even infinite. So we might not know the population size. Like stars, we might not know in the galaxy how many stars there are, but we can talk about sampling a few stars and gathering information by observation through a telescope possibly. But yes, it's possible that a population does not have a fixed size. A parameter is a numerical measure computed from the value of a variable on all items of the population that describes that specific characteristic. A sample, in contrast, is an observed subset or portion of the population with a sample size given by the symbol little n. Okay. A statistic is a numerical measure computed from the value of a variable on all items of the sample that describes that specific characteristic of the sample. Refresh your screen if you don't see what I'm talking about. Okay. So to remember this terminology in English and in French, it's a little bit different, right? But in English, this works. The mnemonic device, P in P, parameters for populations and statistics in samples. It turns out to be the same letter. The goal of statistics is to gain information from data about a variable. If we had the entire population of size capital N, we could compute the population parameters. The sample statistic is intended to estimate a population parameter when it is not possible to get all the population values in a feasible way. So you're going to see me use this example about height of women, and we're going to talk about computing the average height and then something known as the standard deviation as a measure of variation, differences in height for the sample. And we could calculate the sample mean and standard deviation as approximations to the population mean and population standard deviation. I'm going to introduce these symbols. I'm repeating them. I'm going to repeat this, but I'm just showing you now. We're going to talk about this shortly and throughout the course. Population mean, I'm going to use this symbol mu. This is the Greek letter for M. and the population standard deviation sigma, which is the Greek letter for S for standard deviation. Then these are estimated by the sample mean also has a symbol. I'll use a different color. The symbol for the sample mean is X bar, and the symbol for the sample standard deviation is alphanumeric S. Okay, so when I invoke the Greek letters, the Greek symbols, I'll be talking about population estimates, and when I use alphanumeric characters, characters from the alphabet, I will be talking about statistics. So those blue are statistics, and these are symbols for parameters. So they could be averages, standard deviations, and other measures we're going to talk about. So making these calculations, we can use data from experiments. We can also use data from samples. Another example of a parameter of interest could be that the proportion of people that are employed in a country. Proportion or population proportion, I'm going to use this symbol P, which is actually not Greek, but I guess that's one of the few pieces. That's a P. And it will be estimated by the symbol P hat. P with a hat on top, if you can't see it. I'll make it bigger. Okay, so this is the estimate. I'll stick with my color scheme. This is the blue for statistic. Whereas the parameter, I'm going to use red. Okay. So P hat is an estimate of P. So what we have here is a list of the variables, of the statistics that we'll talk about in this class. And there's going to be a few more. We're going to discuss the sample mean, the sample standard deviation, the sample proportion that are used to estimate the population mean, the population standard deviation, and the population proportion. And I provided a few examples. All right, with that, I'm going to turn now to the review of the videos regarding sampling. A population, remember, is the larger group of objects or subjects where the information should be derived. We were interested in gathering information about those subjects. Individual members or subjects of the population are known as the units, and a sample is a subset of the population, which should be chosen carefully to be meaningful or useful. We refer to sample units as individual members of the sample. Now, in the video, can you describe a non-human sample presented and provide me with the information on the population, its units, sample, and sample units. Yes, Ronel, we will be able to use the symbols to make formulas, yes. And we will get to that soon. Tomorrow. I don't think we're going to have time today. But I'm setting the stage because you'll see those symbols throughout the course. All right, so what's an example that you recall? So if you remember the potatoes, okay, if you didn't see it, you'll see a video, you'll see in the video about 45,000 pounds of potatoes on a potato Frito-Lay potato truck. 45,000, sorry, these are potatoes that are brought in a truck to Frito-Lay factory. So it's 45,000 pounds of potatoes in a truck. And the units then are the potatoes in the truck. The sample from the potatoes in the truck, a sample is taken in 5 30-pound buckets. Okay. And then those buckets are studied as representative of the whole truck. And based on the analysis, the quality control conducted on the trucks, or I guess they just call it the sampling conducted on the trucks, the outcome of the trucks, and then the potatoes being peeled and produced as potato chips, the quality of that final product determines whether the trucks are accepted, the truck of potatoes is accepted or not. So that is what happens in the video. So the sample units are the potatoes in these buckets. So the idea of how they were chosen, the selection of the 5 buckets is important, of course, because you want to pick a representative sample. So you could take some potatoes at the front, some potatoes at the back, some potatoes deep down, some potatoes at the surface. You want to make sure that samples are good. Samples that are not representative include, and I provide some examples here, and this was, in fact, there was a company called Briex in the 90s. Briex was a gold excavation company. They were searching for precious metals and gold particularly. And it was discovered that they were artificially inflating the value of shares in the company by producing samples from their mines that had a substantial portion of gold, and they were sending them in for well, I said steel. This was a precious metals company, so in this case I mentioned the steel that they were sending in for testing, and they were sending in these rocks that had minerals in them, and it turned out that they were fraudulent. They were sending in the same samples repeatedly, and this was discovered, and the company had a lot of problems. You can look this up on the internet if you want to know more about Briex and what happened. So yeah, you don't want to do that. It's not representative, and it's not acceptable, right? Samples are not good when you let people voluntarily opt in to the sample. You could have some information there, but you have to be aware of the inherent bias in allowing people to opt in, for instance, in syndicated radio shows where people call in, or when people write in. For example, in the video, the Ann Landers columnist, she was having people write her. And these people are opting in themselves. They could have emotional issues. They could be very upset, or they could just be pranking. You know, they could be pranking the hosts and not be legitimate callers and biasing the results just to make a show on the side of the broadcaster or the newspaper. They don't mind because it makes for sensational news. But in terms of representation, not very representative of topics. It's also not wise to let samples, allow samples to be drawn as representative of a larger group when the sample is an interest group. A special interest group does not represent the whole. Okay. So here's another opportunity for you to do some randomization. Here we have, first I need to talk to you about simple random sampling. So SRS is simple random sample. And it's a procedure used to select samples of size n objects from a population in a way that each member of the population is chosen strictly by chance. The selection of one member does not influence the selection of any other member, and each member of the population is equally likely to be chosen. And further, every possible sample of given size n has the same chance of selection. So this is a very long sentence, but it captures all the properties of the simple random sample. And this one is the least remembered, so I will underline it. Every possible sample of size n has the same chance of selection. Okay, it's really important. It's important theoretically and also practically. In this way, the sample is representative of the population. All units must be identifiable and initially labeled for random selection. Okay, so you don't just choose, you identify your frame, you identify the possible units, number, label them with numbers, and then from those, using a random digits generator, you select a sample. So here's an example. I ask you, choose a sample of size 3 from a population of size 28. Ensure that you have a simple random sample. So I'm going to imagine the numbers between 0, 1, and 28. And I used that 2-digit labels because the last one is 28. All of them have to have the same size label, so the first one has to be the same. Now I mentioned to you, begin with 0, 1 to be clear about how you label. It's possible that you could label starting with 0, 0, but that's not the instruction I gave you. So how will you select? So here's the list of random digits here. I've given this to you. Now you're going to use it choosing 2 elements at a time, 2 digits at a time. So 0, 5 would be our first. The next one is 90. 90 is not in our list, so we ignore it. Either is 75. 0, 4 is in our list, so we'll take it. 95 is not, so we ignore it. 11 is also in our list. And what else? 38 is not in our list. We need one more. No, we just need 3. There you go. 5, 4, and 11 will be selected. Any questions about that? Should I do it again? The next question is, 8 people who suffer from migraine headaches volunteer to take part in a focus group to explore their preferences for over-the-counter medication. So here is the list. I need 4. And that's all the instructions I'm given, correct? I'm not given instructions on how to number these. I could number them, well, since there's 8, I have 2 options. I can number them 1, 2, 3, 4, 5, 6, 7, 8, in which case which ones would I select? I would have, going one at a time, there's no 0, there's a 5, so I select 5. 9 is not one of them. 0 is not one of them. The next one is 7. 5 is already selected. 0 is not one of them. 4. 9 is out, 5 is out, and 1. Do you see? So I got 5, 7, 4, and 1. So 5, 7, 4, and 1. So Chang, Miller, Reed, Toman. So that looks like B. But I tell you below that the answer is E. So this is sort of a trick question. This is sort of an instructional exercise to demonstrate that the way I label will determine my sample. All right. So if I labeled, obviously, if I labeled this differently, and there's two different ways I could label. I could label using 0, 1, 2, 3, 4, 5, 6, 7. I could start with 0, why not? And I could use 2-digit labels as well. 0, 1. I could, it's not wrong, as long as I do it correctly. As long as all my digits are the same length, all my labels are the same length of digits. So you'll see if you use this labeling scheme, you'll get a different answer. And this labeling scheme will give you a different answer. And it turns out that all three, B, C, and D, are possible answers. Now this happened because I did not provide you with instructions on labeling. Okay, so that it's not wrong to use either one of these. It is wrong to say that you can only use one of these. The truth is, without instructions, all three are fine, and E is the best answer. So without precise labeling instructions, all these answers are possible. Do you want me to show you how I get those answers, or do you see with you can do this yourself? The solutions are also provided in the annotated notes. Annotated notes are in the course platform. Okay, no comments? Now it's really important to remember that labels have to be the same size. This ensures that when you use the table, you take digits of equal length, because digits of equal length, or labels of equal length, have the same chance of being selected. So when you use the 10 digits 0 through 9, each has 1 in 10 chance of being selected. Doesn't matter the value, what matters is that it's the same and equal throughout the possible digits. Similarly, if you use double digits, the possibilities are 100 pairs, right, from 00 to 99. Again, each has 1 in 100 chance of being selected. This creates independence of selection for each set of digits, Okay. And then I have provided some explanation of probabilities that you can read. So just read this, self-study this. And let me know if it's confusing. If you have any questions. So the main thing is that you label all population units first, and then all labels with all labels of the same length. There are two types of simple random sampling. There's sampling with replacement and sampling without replacement. In sampling with replacement, after an element has been selected, it is returned to the frame and is eligible to be selected again. In our case, what we were doing by selecting a participant only once, even though their number reappears, that would be sampling without replacement. Sampling without replacement, the one we're using, is more common than sampling with replacement. Okay, so now I want to talk about, if you don't have any questions, is what was introduced in the video about, just sets of videos, about stratified. Oh, I have some questions. In exercise related to simple random sampling, why did you consider the first three numbers in the range? Why not 4 or 2? Let's see, what did I do wrong? 4 or 2. In the first one, it's just because it asks you for 3. It's just that was the instructions for the first one. Is that answering your question, Jean-Carel? Okay, and Samuel Bernard, I answered your question in what I just said. We sample without replacement. Once someone is selected, we don't select them again. Okay, it's not practical to ask the same person to be a volunteer in the same study. So we conduct a simple random sampling without replacement. Very good. Good question. Thank you. Okay, so read through this and let me know if you have more questions, and we can talk about it tomorrow or later today. Well, we only have an hour left. Okay, good. Okay, so this is another thing you need to know, is that a probability sample is a sample chosen by chance where we know what samples are possible and what chance or probability each sample has. I'm going to not highlight because it's making it messy. I'm just going to show you. Now, a simple random sample has a stricter requirement that each member of the population has equal chance to be selected. Okay, so a simple random sample is different from a probability sample. A probability sample, it just requires that each sample has the same probability. of being selected. Simple random sample adds that each member of the population has equal chance of being selected. Okay. Oops. So I just want to underline the difference between a probability sample and this point. Simple random sample, each member of the population has equal chance of being selected. But for a probability sample, it's that requirement about each possible sample has the same probability of being selected. Okay, so where that brings us is two more kinds of sampling design that were discussed in the videos that are very important and used widely. One is stratified sampling, and the other one is multi-stage. Stratified, or stratum, are used to divide subjects or study subjects along a characteristic that creates systematic differences between the groups. So, for instance, in the video, you learned that the survey they were discussing wanted to look at households and was aware that information on labor and employment was significantly different in rural, suburban, and urban communities. So if you, for instance, if you're interested in unemployment could be higher in rural communities for the lack of industry in the rural community, and higher in the urban communities. So rural communities across a region or states or a nation, they'd be more similar than they would to the other groups. So it could turn out, because there's less people in a rural community, if you didn't pre-stratify, you might end up with a sample that has no rural households in it. So because you want to be able to report on rural communities, suburban communities, and urban communities, because they're distinct, instead of sampling from a region at large or a nation at large, communities are counties. In the U.S., it's counties. So what you would do is divide up all the counties into rural, suburban, and urban, and then sample among the rural communities, sample among the suburban, and among the urban. Okay, so this is like blocks in that I want all of them represented in my study, and I do not want to run the risk of losing information about the rural community because maybe there's much fewer households in rural communities than there are in urban communities. let me read through this. Sometimes we know there are systematic similarities between groups like men and women, or rural, suburban, and urban. So rather than get a simple random sample of the entire population, it would be more efficient to get a random sample, simple random sample, for each stratum, or all strata. We then combine these simple random samples to form the full sample. This is referred to stratified random sampling. Okay, so you would pre-specify and select among rural, select among urban, and select among suburban and among urban to conduct a study or a sample. So the challenge will be in determining what is the adequate number to sample from each and gathering all the information to create the frame for rural and sampling within suburban and urban. Combining the data may be a challenge as well to make a representation of the nation, but at least you'll have information on the stratum, and then you can hint at estimates for the larger whole. So I mentioned the disadvantage. Well, the advantage is this is more representative of a sample, and the disadvantage is it might be costly or technically difficult to combine those in the end. But it would be more meaningful to do, and that's the greatest advantage, because you would represent all the communities. Now, this is different. Stratification for representation is different than multi-stage sampling. If you guys are copying what I write, just take a screenshot. Most of what I write is already in the notes. I'm just emphasizing. Okay, now multi-stage samples, I explained, are different. They have a different motivation. Multi-stage samples are employed when it's difficult to get an adequate list of the population frame. Okay, so it's hard to get a list of all the subjects that you want to sample from. And let's say, for example, we wanted to sample households. So we've determined that we want a sample of 1,200 households in a country so that we can study their consumption of whole foods, fruits and vegetables distinct from refined food products. Now, in the country, there are 18 million households, let's say. But we only have enough money, we only have a budget to interview 1,200 households. So how should we pursue this study? We could get the list of all the 18 million households and start labeling them 000000001, 0000002, etc. and sample from those. But we run a risk that identifying who lives there is going to be difficult. It's very hard to get a list, an up-to-date list, an instantaneous list of everyone at a snapshot in time. And by the time you make the list, the tenants, especially since there's 18 million households, may have moved or changed address. Now you could just do this working with the active tenants or house people in the household, but it's difficult still to get this list. Okay, there's not a list floating around that you can easily acquire. So this is expensive to obtain. It would be much easier, and with a limited budget, which most of us face, it would be easier to conduct this study. But there's not any issues, other issues that we're concerned with, and I'll get back to how this ties in with stratified sampling in a minute. If this is our main concern, then why don't we consider instead a frame that of units that we can label easily and begin with that. So for instance, in this country, why don't we identify the regions of the country? So let's say in Puerto Rico, there's 78 regions, but okay, so in a small country, let's say there's 30 regions. And these are known regions. We label them, people know them by name, okay? So they're very well known. You can list them out by name and label them. Right, all the way to 30. And I'm just going to say, region, well, I'll just leave it like that. So region 1, 2, 3, and up to 30. And what we can do then is take a simple random sample of these regions. Let's say from 30, it's determined that it will be adequate that 10 regions are selected. So 10 regions from the 30, using a random digits generator, we would take just 10. All right? So that would be known as stage 1. Once we're done stage 1, we move to stage 2. We identify in each of the 10 regions all of the communities in those regions. There's 10 regions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of the 10 regions has, for simplicity, let's just say there's 30 communities in each. Okay, so there's 30 communities. So we started with 30 regions. We picked 10, and then we have to pick from each of these having 30, we need to choose, it's determined that we should pick or sample 20%. So what we're going to do is for each of the 30, we're going to label 01, 02, again, the same thing, 03, all the way to 30, and we're going to randomly select 10. So from 30, we choose just 10. So we're going to have 10 more, so 10, 10, 10 for each of these. So what do we have now? Oh, sorry, I said 20%. 20% is, 6. We're going to choose 6. I wasn't reading it properly. I was forgetting. Okay, so it says here 20% of 30, which turns out to be 6 regions. So we're going to get 6 from each. So 6, 6, 6, 6, all the way. So we pick 6. So it's going to be 6. and I'm not going to draw this all, but you get the idea. So from each of these 6, these are communities. There are 200 blocks. There's 200 blocks of each of these. And what I'm doing is I'm trying to get closer and closer to households. First, I go to blocks. There are 200 blocks on each of these in each of these communities. So I need to label all 200. So the labels will look like 001, 002, all the way to 200. And I want to randomly sample 2%. 2% of 200, 2%, 2% of 200 is 4. All right. Questions so far? Do you follow what I'm doing? I'm just repeating the same thing at different stages. So there's going to be, out of 200, for each of these communities, there's 200 blocks, and I want to sample 4. Now, this number 2% was predetermined. I'm not making you calculate it. I'm just giving it to you. But someone calculated it. Someone told us that that's a wise idea. So we're going to use it for our study. Okay, this is just a hypothetical study. So we're going to choose 4. So far we have 6 times 10, which is 60 communities. And we're going to pick from each of the 60 communities 4 from 200. So we're going to have 60 times 4 or 200 blocks that are selected. Finally, on these 240 blocks, there are going to be 100 households each. Now, I've simplified this to make them all equal, but I hope you can understand. What we're interested in is a fair sampling that's determined by a qualified statistician. So we're going to say with 100 blocks, 100 households on each block, 5% would be sufficient. So 5% of 100 means 5 more. So what you've done is now chosen 5 from 240. Well, 5 times 240 makes the 1,200 households. And each time, from regions to communities to blocks to households, we have an active living list of what those are. And so it's easy to make a label. Easy to label and easy to randomly select from those stages or at those stages. And then these 1,200 in the end will be the households interviewed. It didn't require us in any way to find 18 million households. We just had to repeatedly, in succession, approach the level of household. So what's the advantage? The advantage is you avoid the cost of identifying and numbering all units of the population in order to conduct a simple random sample selection. And the disadvantage is you have to hire someone who's going to help you come up with all these percentages of how much to pull and then help you roll out all the numbers in the end to draw your conclusions. Okay? So This is known as multi-stage. This is different, has a different motivation from the stratified sample. Stratifying is to ensure representation. Multi-stage is to avoid problems resulting from having to identify and number all units in the population. So both of those problems are those problems are common in studying populations, large populations. So often you'll see census data for samples is collected with both multi-stage and stratified sampling. So what we do with the multi-stage, occurs after you've already stratified by rural, suburban, and urban, for instance. Okay? So you can have both. And I ask you some more questions about what's an example of multi-stage sample, and then again, that's the NRRC survey, I believe. All right, we are almost done here. We've really done. We're finished early. Well, I guess I'm going to finish, but I want to say some things about tomorrow's class. In deriving statistics in the arena of business and economics, we're interested in quantifying response of individuals, consumers, business owners to surveys. There are different types of problems that in surveys that may lead to systematic bias. These are known as non-sampling errors in surveys. So when I refer to sampling errors are the result of the fact that you don't have the population, okay? So your estimates will not be exactly the same as your population parameters, your estimates of statistics. Sorry, your statistics that estimate the population parameters will be wrong, right? They'll be off. They could be off, and those are known as sampling error. But non-sampling error were described in the videos. So these include undercoverage, where people are just plain missed. Okay, where you miss your target population. That can occur if you conduct a telephone survey with people who have landlines, and you miss people who don't have landlines, and that's more and more the case because people have cell phones, not home phones. So that is undercoverage. Non-response bias affects your survey responses when a segment of the population does not respond. So I mentioned the problem with the polls for a president in the United States, where survey subjects didn't want to reveal their approval of Trump, and so distorted the results, made it look like he was less popular than he actually was in the first and second election. Also, difficult for sensitive issues to get response. So private question that people don't like to answer is income. It's very difficult to get answers about income from people. That's why qualitative questions categorizing income are used often because people don't want to reveal, expose exactly the income that they make. It's a sensitive type question. Response bias is the flip side of non-response. This is where a segment is more likely to respond. So as I mentioned before, people might opt into a survey because they're passionate about an issue, and they'll distort or bias the result of the survey in their favor or towards their opinion. Response bias can also occur when a person being interviewed doesn't like the interviewer, might find him suspicious and doesn't want to reveal information. That's non-response. But response, yeah. I'll take that as the identify. If they really like the interviewer and they reveal more information, that's a response type bias. There's a website called ratemyprofessors.com as an example of a site where students opt in and write comments or review professors. And there you'll see definitely response bias, students who are really happy about a professor will write about them, or really disgruntled. You'll have your extreme results possible, on that site. Voluntary response samples are riddled with response bias as a consequence. This is because people with strong opinions, especially negative opinions, are more likely to respond. Convenience samples might also suffer from response bias. These are samples collected by, like, let's say on the street, or like in the video you see the interviewer just hanging out and asking people who are passing by questions. That's different than voluntary response. Voluntary response is more when someone is has either posted in the newspaper, or like we explained, written into a newspaper column, or called in on a radio talk show and expressed their opinion. Convenience samples are collected when somebody just passes by and an interviewer approaches them and asks them questions. So this could be biased by the interviewer selecting more approachable people. Actually, if you conduct a survey in some of these malls or strip malls that you find in North America, it's common that seniors will go early in the morning, and even currently with the pandemic, there's actually hours set aside in the morning for seniors to shop. And so if you have a survey for individuals in the morning hours, you're more likely to encounter people who are seniors or retired. And if you were to ask them something like, what's your approval of rollerblades in the mall? If you ask them in the morning hours, you'll probably find less approval. It'll be biased against rollerblades being used than if you ask the question at a different hour in the afternoon or evening. It's important that surveys reflect the target population. You're going to ask questions of the appropriate population, right? That's clear. So if you want to know about, if you want estimates of individuals providing charitable donations, you shouldn't be conducting surveys on university students because they aren't likely to give to charities. Another point that contributes, another factor that contributes to non-sampling errors and bias are the wording of questions. Survey questions must be written to avoid confusion or ambiguity and avoid manipulating the response. So, for instance, if you want people's public opinion about building a new stadium with municipal dollars, with tax dollars, asking a question like, are you interested in a new stadium is less manipulative than this more slanted question. A new stadium is what San Juan needs to be like other capital cities. And you get them to say yes or no. Another example, and this one happened to me. This is something that happened to me when I was working on my master's in graduate school. Someone had approached me in the cafeteria and asked me if I would participate in the survey. And I thought, well, I'm studying statistics, and I appreciate the importance and interest of surveys, so I decided to help the students. And I found myself responding to a question that took me over 45 minutes to complete. And it was pretty clear that the survey was about my relative patience, about a number of things, how calm and patient I was. And I realized that the student, well, I actually thought he was joking. I thought it was a candid camera or something, if you've ever seen those. Because the student was asking me to answer a survey on patience. He was trying to quantify the degree of patience students had. And the only person that would answer this type of a survey that took more than 45 minutes would be a patient person. So he was only really going to be able to reflect the behavior of already patient people. So this would it would bias his results. Depending on what he was looking for, it definitely would bias towards the behavior and attitudes and preferences of people with patients and not the general population. So this would create error in his results. I told him, and he didn't seem to know what I was talking about, so I knew it wasn't a candid camera. All right, so that is that. What you have next, well, I just mentioned here, sampling error, which we will talk about. The fact, as I mentioned, the fact that we are using a sample and not a census means that our results will be different, likely different, than if we had the full population. And we refer to the difference creating a sampling error. Errors which are not related to sampling may occur at almost every phase of a survey. Interviewers may misunderstand instructions. Respondents may make errors in answering questions. The answers may be incorrectly entered on the computer, and errors may be introduced in the processing and tabulation of data. These are all known as non-sampling errors. I already described those. And really, that's it. So what you need to do next is work with the homework that I set up for you. I'm going to just show you, give me a minute, and I will show you our website. Again, I'll have to log in again. I got locked out. Okay. One minute or half a minute. That's not it. Okay, that's it. I have to make this fit. So this is the Comunidad website, and I understand all of you have been able to access it now. Please tell me if that's incorrect. Please let me know. Sorry, I'm having trouble. I need to figure out how to do this in a standard way. Okay, so there's the website. And what you need to do, now that we have discussed design of experiments, oops. Oops, something happened. Hold on. Hold on. I have some time to fumble. Do that again. Jeez. There it is. Okay, so you're going to look at the lecture notes. Okay, well, that's what we just did. You're going to look at the annotated notes. These are the notes with the answers that we've discussed mostly. There's some that I didn't. I just left them for you to look at. You will do complete the homework, try the practice assignments, and the quizzes, and then you will be done with DNS. And let me know any questions that you have. Write me an email, and I'll fit them into the next discussion. Tomorrow, we're going to begin with the descriptive statistics. The lecture notes are here, the annotated notes are here, and the sample problems. You need all three documents. Well, sorry, you only need two, one of these two. I would say use the lecture notes and the sample problems for tomorrow. Print them up or have them ready. That's what we're going to discuss. Anything that we don't complete tomorrow, you can watch that information in the videos here, and that's what I will leave off with tomorrow, because I'm sure we won't finish the whole thing in 3 hours. Any questions? Any questions from anyone? Can the sampling error be caused by lurking variable? Well, remember, the lurking variables are in the context of attributing causal effect. So sampling error, well, it depends what you want to do. So you're talking about the sampling error. Sampling error is due to the fact that you are using a sample and not the population. That's really what we're talking about with sampling error. That's my best answer for you. Sampling error results from using a sample and not the entire population to compute parameters. For using a sample to compute statistics and not the entire population to compute parameters. So you're going to have the error. So let's say it's true that, what can I say? Okay, let's say we conducted a sample. Let's see, wait. Okay, so the question, let's say we're interested in answering the question, how many people like soccer? So how many people like soccer? Something very, very general like that. And it turned out that in a population with 50% females and 50% males, I say there are 50% females in the population, and men tend to like soccer more than women. I could be wrong in certain countries, but I'm just going to make a bold statement. So 50% females and 50% males in population, and men tend to like soccer more than women. So it turns out that it might look like let's say 45% of men like soccer. Okay, I'm going to make this complicated now. So the point is, if a sample has more women than men in it, I'm typing as I'm speaking. If a sample has more women than men in it, it will look like less people like soccer. Okay, so this would be an error, and this is known as sampling error. The fact that you used a sample that wasn't perfect, it wasn't exactly like the population, created an error. Any other questions? Oh, good. I'm glad you understand. Okay. Lurking variables are used mostly when we explain the true cause of an effect, okay? That's what lurking variables are used to describe, where we can't really identify it, we can't put a name on it, but we imagine it's there. A third variable, they mentioned in the video. A third variable, when talking about smoking, it was to say that it could be the case that people who choose to smoke actually are predisposed to cancer. In that case, it's not smoking that caused the cancer, it's just that they already were predisposed to get cancer. That's a kind of lurking variable. Genetic factor would be a lurking variable in that case. Okay, there's my statement. Genetic factor being a lurking variable proposed by people that claim that smoking does not cause cancer. So it's intended to explain a relationship. So it becomes an explanatory variable. Explain, explanatory, convenient choice of terms. Okay, if you don't have any more questions, I am going to go for the day. And I'll see you in the morning, right? 9 a.m. And we will start with, I'll start with graphing, and then I'll take your questions. Sorry, graphing and descriptive statistics, GDS, and I'll take your questions as well. I'm going to try and track down Laurent. If any of you can communicate with him about setting up a Zoom, we can try that tomorrow as well. I I'm willing to try it. I just don't want to waste time with it if it doesn't serve purposes. I find that YouTube is rather seamless for me. But if it doesn't serve you and you'd really like to meet on Zoom, I'm going to try that. So can I say good bonsoir? Bonsoir. Till tomorrow. À la prochaine. I'm remembering all this. Thank you for your patience. Thank you for your perseverance. We will get through this course. Have no fear of that. See you soon. Thank you. Bye-bye. And study tout le monde. À demain. Bye-bye. Ciao. Thank you. Bye-bye, Anna.